Who was this?
It was me.
Okay, excellent. Thank you so much. I think we're gonna do it like the airplanes, where where the pilot confirms if if everything is in place. I think that's the way to do it. Brilliant. So I'm gonna start 2 minutes early. Thank you very much once again, everyone, for joining us today. This is session 3 of your course production at DSI. Yesterday's meeting, we went a little off track, so I'm gonna start with Python today. So I'm gonna invert the order such that we get a good chance to look into data engineering. Then we will proceed with the scheduled lecture that we had for today, and probably, depending on how well we do, we we will go back to Python and see the first notebook related to sampling. I don't expect that it will take us too long. It's a very simple notebook. And then next week, we're going to continue with notebook number 3B. So we're a little delayed, but the course is also thought that we will get into delays. Okay. Before we start, I want to make a couple of notes. I had a few conversations with some of you. Some of you were part of it, and then some of them were after class. And I got very good recommendations from a few of you, and thank you very much for sharing your thoughts. I'm going to repeat what I said at the beginning, and I think I need to reiterate it every session because we need to understand what we're here to think about. The most important part of this course, and when I say most important, is in terms of your professional development, meaning the way you will go out and get a job, the way you will perform a job in a data related field is by understanding ideas. Okay. We're not here to follow recipes. Recipes will not help you get anywhere unless you're a cook. And even if you're a cook, probably they will get you as far as McDonald's. We are here to think. We are here to understand ideas, learn a few patterns, and as we get comfortable with the techniques that we will be discussing, we will play around with them. I know there are some musicians in the room. This is the way musicians do their craft. They learn the technique, they get really professional about it, and then they spend some time playing, improvising, right? That is how you hone a technique. When we do the theoretical discussions, I think this is very simple because I discuss ideas and you only see ideas. There's nothing for you to do. But when we discuss code, you have the entirety of code, right? You can run it from beginning to end and see if it works, see if it works for you. What I am doing in class is I am explaining how to understand the code. I am translating Python into English, and the exercise is not trivial. This is one technique that one can use to actually learn how to code. Um, Many times when you read books, when you have manuals on how to learn how to code, code, what they recommend is actually add comments on the side of the line describing what each line does or what each chunk of the code actually does. And that is what I'm doing live. In addition to that, I will make mistakes. We all make mistakes, right? And part of learning how to code, this part is learning how to interpret the error messages that you get. And that is another part where I stop, I read the message, I say, hey, this is the way that we are going to understand it. Okay. And as well, I walk you through my debugging process. This is not the only debugging process. This is my debugging process. I'm sure that many other developers use of something similar, and then many others will use something different. Um, but it is important to know how to walk yourself out of an error and as well distinguish the qualities of your error, right? Sometimes we get some warning message, and the question becomes, do I need to worry about this warning? And the answer is maybe. It depends on what it tells you, right? What is it warning you about? If it is an error, it is most definitely an unhandled exception. And in that case, if you want to do something useful with your code, then you need to resolve it. And that is the process of debugging. Okay. So if you're an expert coder, I'm sure that you will be able to follow. You can use the live notebooks, type along. If you type fast enough, you need to type fast enough, not because I type very fast, but because I'm not typing my code. The code is already written. I'm just copying and pasting. So that is super fast, right? So don't try to keep up. That is the reason why I say you have the recordings. What I would recommend you do is, and in general, if you're an expert or non-expert, is look at the idea, listen to the discussion, understand what the lines are saying, try to read them as if you were reading a set of instructions. The most important part of this course, in my mind, are actually not the notebooks. They are the code snippets or the code examples that I left in the 05 source folder. Okay. The the other thing that I need to announce is we had a glitch yesterday. We just discovered the mystery of where our recording went, and it turns out that there is a recording, but we just didn't know where to find it. Now we have happily found it. We have made, nevertheless, available to you the recording of the previous cohort. Right. That means that you can review all of the concepts. As of tonight, that we reviewed yesterday, it was just the version that we did a few months ago. Nothing changed from the slides, so there is no discrepancy. Today, given that yesterday we were a little sidetracked in our discussions, I will start with Python. So I will start with data engineering, the second notebook. I will proceed then to discuss the slides that we had planned to discuss today. And as I said, we will do most likely the first notebook in notebooks of the set 03. Okay. Um, as well, I'm going to change a bit of the dynamics in terms of question answering. I will make pauses with the explicit purpose of allowing discussions in terms of question and answer. I would appreciate if we keep the question and answer period to question and answers that are relevant to the course and specifically to the course content. If you have complaints, if you have grievances, there is an appropriate place for you, and there is an appropriate place to express them. You can always schedule a call with me. I'm more than happy to jump into a call. If you need to bring in Jeannie, or if you need to bring in Rohan, you're more than welcome to. Or if you want to have an independent call with them, that is also a possibility. In addition to that, if you don't think that your concerns are as grave as to require a meeting, I understand that there's also surveys where you can express your opinions and provide feedback in terms of what needs to be changed and so on and so forth. Okay. I'd say this because we are delayed and there's a lot to cover. I appreciate that we're going fast. I sometimes start the course by saying this is like going to the gym. And if you go to the gym and it doesn't hurt, you're really not going that well to the gym. So it will hurt. Growing, acquiring knowledge does take effort. It's not a happy place. If you are used to watching YouTube instructional videos and you're not expending a lot of effort, it is very likely that you are not really learning that much. You're just getting entertainment. So that pain that you feel, that frustration that you may feel, it means that it's working. And as I said, it's like going to the gym, right? So it will hurt a little, but I'm sure that next week it's going to hurt a little less. And if you continue doing so, then it will become part of your daily routine. And then one day you will be having Python for breakfast. Okay. So I hope you have a good session today. Let's start with Python. Okay, I'm going to take it from the top. This is the notebook number 2. We're not going to use the credit data just yet. I think I saw a message that somebody needed a copy from Kaggle. We'll make it available to you most definitely. What we're going to work with today, there is the stocks data set. Okay, so yesterday I said we only need the stocks data set. There's about 5,900 files, a little less, 500 and 884 files. You can see them here in my file folder. The folder should be under the directory 05 src, then data, then prices underscore CSV, and then stocks. Okay. Um, okay, so let's start again. Okay, the first thing that we do, as we always do, is we load our environment variable. Okay, I got this message. Notice what I see. The .env extension is already loaded. To reload it, use reload extension .env. Okay, this is a Jupyter Notebook thing. Percentage will sign will give you access to load within the Jupyter Notebook environment a certain set of libraries and use them as if they were part of the Jupyter Notebook environment itself. If you get a message like this and you're concerned, and sometimes you should be concerned, the easiest way to get rid of it is restart your kernel. Okay, so the kernel is a Python core that is running underneath the Jupyter Notebook. And the Jupyter Notebooks are built on top of something that resembles a web server. Okay, so there is something already running Python underneath, and that something will execute your Python code. When you click restart, basically what you do is you disappear that kernel such that it forgets everything that you have done. Okay, I will clear my output, and this is just for good order. I don't I this is just my personal opinion. I'm not too crazy about Jupyter notebooks because they can induce mistakes in the things that you are doing, right? In my development process, I generally start with a Python script on the side, and if I need to draft some code, I draft it in Jupyter Notebook, and immediately after, I transfer it over to my Python script. Python scripts can be very well maintained. They read very well on GitHub, and I can control the changes and be mindful of what I'm doing to my code. Whereas in Jupyter Notebook, you may have a bit more difficulty in doing that. As well, when we log items in Python code, we know exactly where we need to look. And finally, if your code becomes sufficiently complex, we may benefit from organizing our code in smaller components, in smaller modules. So Jupyter Notebook don't help us for that. They don't act as modules. So as you are progressing in your development career, I would recommend that you start making it a habit of having a Python file on the side to actually start transferring your code from one side to the other. That is my my recommendation. The Jupyter notebooks, don't get me wrong, are a great place to start. You get immediate feedback. They work like an Excel. They're good enough for that, right? And they're good enough for the documentation. They're a perfect place to write down your ideas. I think that this model can work because I read in this paper, and this is the link to the reference that I'm using, and so on and so forth. And therefore, you can see in this graph, and because of this, I made this choice, and so on and so forth. Perfect. But it doesn't end there. That is your notebook. It's literally like a notebook, and nobody, I think, ever submits a notebook as actual work. Okay, so let's start again. We run this. We have loaded our environment files. We discussed this. Now, we didn't have a lot of time to go through the diagram, but the diagram is an interesting diagram. This is a standard architecture in data engineering, right? It is called the medallion architecture, or you will find it by different names. I think that the most common one is called medallion. It generally includes three phases. There is an ingestion phase. Sometimes it's called the bronze phase. There's an intermediate phase. Sometimes it is called the silver phase. And there's a golden phase, or the Mart phase. And the idea is that you have data in the world, right? So these are your files. These might be other databases that are within your organization. There might be some streaming data. There might be some data that you acquire through an API, and you need to land it somewhere. That landing database is called the bronze layer. Nothing other than a reflection of what you need. Okay, so you go to your finance data set database over there, and maybe you go to your prices database on the other side, or if you're in healthcare, your patients database, or your treatments database, or your pharmacological reference set, and so on and so forth, and you land it in a place where you can control. Okay, so this is where it starts. You write some code and you transform it. Usually, you will require a few intermediate transformations. Things like I got the dates, I want to put them in the appropriate format, right? So I got the dates, they are strings, and I want to convert them into a date data type. I got data that contains missing values expressed as quote unquote. And I may want to convert that to null, a proper expression of missing values. So these type of transformations occur in the silver layer. And then generally the gold layer or the final layer, marts are called in the DBT literature. Um, they are the things that either you yourself will use as a data scientist or your users will use, right, as users. So we had a discussion yesterday. If you're building BI solutions or business and intelligence solutions, generally you follow this pattern, and what your consumers will see is this. In addition to this, you can create a nice semantic layer, right? So you can give it meaning. When anything has the word semantic in it, it means that we're talking about meaningful things. And things are meaningful when we can ascribe an appropriate name to them and we can describe them, right? We describe data using metadata, right? So we can start with the column names, of course, that is very obvious, but then we may add descriptions, we may add some statistics like freshness, when was the last time that this data column was refreshed, how many missing values do we have, what is the ultimate source, and so on and so forth. Okay, so these are the things that you connect to Power BI, Tableau, Polymer Search, and so on and so forth. This intermediate layer, its only purpose is to produce a gold layer. So you can make this ephemeral if you need to save some space, or if you don't really want to write it, you can perhaps even start thinking of writing these as views in the SQL language. Okay, so these things generally you land, you write to a database. These things you sometimes write, you sometimes don't. It depends on how much time it takes you to construct. These things generally, just to provide a very good user experience, you actually write. Okay, you don't need to write them. If the data set is sufficiently small and your database server is sufficiently powerful, you can simply write this one and take it all the way to the back using only views. But that's just a special case. I've actually not seen it very very commonly. Saad, please.
So, so we are writing a backend and we're connecting it to Postgres in our case. We set up the Postgres table like however it needs to be, and then the silver layer is basically a code on either Postgres or Python layer, or is there a definitive?
That is a very good question.
Yeah.
It can be SQL code. It could be SQL code. There's an issue with SQL. SQL is difficult to test. SQL is difficult to maintain and deploy above all. Deployment, remember, is the process by which we have an idea, we experiment with it, and then we make it available to our users via deployment into a production system. So what is happening in the world right now is that you combine Python with SQL through a system or a library called DBT, Database Transformations. Okay, DBT, and I highly recommend if you're into data engineering that you look into this. Works like an intermediate layer in which you can write code both in Python and YAML files, a bit of SQL, and it uses a templating system called Jinja. Okay, so you can make dynamic queries. You can do for loops within your queries, and instead of writing 25,000 queries, you write a single for loop that embeds the queries, and it just runs sequentially. Okay, it does offer a facility to test your queries to see that everything is consistent and coherent, and it automatically produces documentation about your data model. I said a lot of things, and it's a very powerful system. There is an open source version, dbt community, and there's a cloud version, dbt cloud. And the most important thing is that it is SQL compliant, meaning that it can work with any underlying system that understands SQL. It can be, for sure, Postgres, but it can also be Databricks, it can be Spark, it can be Hive, it can be a whole bunch of different things, SQLite, and so on and so forth. So if we go by the idea that we want to check out code from GitHub, we want to make modifications, then we run it, dbt will communicate with your database server, and that is what is going to make the modification to your stored procedures and your views and your tables and your structures and so on and so forth. Okay, so to answer your question shortly, Zad, yes, use SQL. My recommendation is don't go that path. Spend a little more time, learn dbt, and that is a really good solution. Okay,
Thank you.
my pleasure.
And both
So,
are libraries, right? Python libraries.
so dbt is a library that runs a bit like a service, right? So you do dbt build, dbt stuff, but it is written on Python, and the code that you do is in Python. Python
Okay.
plus SQL. Okay.
Thank you.
Patel, please.
Actually, I don't have a question. I just joined middle of the part. Can you just let me know what the figure is showing? Tell me in the brief way.
It's a medallion architecture.
Sorry.
It's a medallion architecture. Sorry,
Okay.
I will skip your question. That took me about 10 minutes to do the explanation. So I would encourage you to look into the video.
Okay, so this is the architecture, right?
It is a plan of what we're going to do. We're going to
Okay,
land the
okay.
data, transform it, and then transform it again.
Okay.
Divita, please.
My question was about the data modeling aspect, like in this diagram. I understand there are 3 levels. So are we implementing, is there a need to implement data modeling at every different level? I know you mentioned the tool DBT, which I haven't used, but also like how would that be different from like traditional dimensional modeling?
You can use dbt to create dimensional models, but you can use dbt to create whatever data model you want within the SQL space. So the data model, dimensional modeling is just an idea of how to create a model. You can, as I said, you can implement it using dbt or SQL or whatever it is, Power BI and these tools, or you can create something else. It doesn't need to be a dimensional model. It can be, for example, a feature store. And this is the reason why I bring it up here. When we create a feature store, it means that we're going to create a data set that is amenable for modeling. Okay, so in modeling, we have features and we have target variables. So instead of creating a dimensional model, what I'm going to do is I'm going to download a whole bunch of data. I'm going to create some intermediate transformations, very simple transformations, and then I'm going to leave it in a place where our model can take it, understand it, and work with it. It will be denormalized. It will be consistent with the shape that scikit-learn actually requires. Okay, so in this specific context, we're not building dimensional models. Okay, any other questions? Sat, you have another question? No? Okay. Okay, this is actually the idea, right? So there's a certain source. In this case, it was Kaggle. Back in the day, it was Yahoo Finance, but it can be any source, right? So we download and store the data. That is where we land it. Then there is a certain data movement and transformation service. And I do want you to start thinking about services, right? Whenever you see the word service, it means that there is a server that performs this activity, right? We're building machines that act on their own. So there will be a certain server that moves and transforms the data from source through the different stages, right? So there is a transformation data store, and then we will get some features, returns, and such. Okay. Now, we did this yesterday. I'm not going to repeat it. Basically, I'm loading my my libraries, pandas, OS, sys. I add my sys path which is the path that will take me to the source directory, which is 05 src. And I do that because I want to run this line. Okay. This line will give me my logger. I instantiate a logger, and I store it in logs. I said yesterday when,
Jesus,
yeah,
I'm having issue with this line. Can you please send me? Yesterday I was not in the class.
oh, you want me to explain what this line is?
No, I am trying to run the cell, but I am facing some issues, so I am not sure how to map this source
Okay.
directory to.
Could you
Yeah.
please address it with one of the learning
Yeah,
supports?
Tajinder, I sent you message in the chat.
Excellent.
Okay, awesome. Thank you.
Thank you. Okay, so what this happens is we add the syspath, and then I wanted to add this thing. A single underscore at the beginning means that this is a private object. I don't intend for this to go out to the world. But the other thing I wanted to highlight is this other thing. Anytime that in Python you see an object that is named underscore underscore, a word underscore underscore, it means that it has some special property. Python uses it for something. So generally it will indicate, for example, in this case, who is calling the logger, who is calling the function. So if the logger is being called by the top level call, meaning I call it from the CLI, or in this case, I call it from Jupyter Notebook, name will be either main or the kernel identifier. If I am calling my logger from within a module, then name will be the name of that module. Okay, so it is who is calling me, right? So who is executing this part of the code? And that way, I will know where in my stack I am calling this log form. Because as you are building more complex code, you will lose track of at what stage your code is running. Now, it doesn't need to be name. I can use whatever name. I can call my logger whatever name. I can call it, this is my logger, right? Something like that works. Actually, it just needs to be a string, right? But the most of the time, and I think this is the thing that I have found most valuable, is actually to call my logger using underscore underscore name. We will encounter underscore underscore name once again when we review the code in the Python format. Okay. So then, what we do is we use glob, and we discussed this at length yesterday. This line will give me all of the CSV files, right, that are contained in the stock data folder. So in prices.csv underscore CSV stocks, all of these files are there. Now, yesterday we discussed as well that if you are working in environments in which you may need to share your code with other people using other operating systems, using os.path.join will give you the benefit of not needing to decide what the level separators need to be, right? So it can be double backslash. In this case, I'm working on Windows, but if you're on a Mac, most likely it's going to be a forward slash. If you're working on Linux, definitely it's going to be a forward slash. Okay. Another thing that I forgot to tell you yesterday is keep your lines not extremely long. Code is much easier to read if you span more or less the length of a poem, right? So in this case, I can add enters, right? Enter. And you can probably start seeing that there's a bit of a structure in this, right? So I am describing a path, and it starts with something that I get from my environment, and then I start adding things. Anytime that you open a parentheses in Python, it will allow you to add a line break and nothing will happen. You can do this for readability. As well, you're writing your code for people to understand, right? So if you think that it makes it easier for your colleagues to understand your code, if you add a little line break, perhaps indentations and so on and so forth, I strongly encourage you to do it. Okay. So we have the stock files, right? So if I assign this to stock files will contain all that list. And then the thing that I want to do is select 60 files from that list of 5,884 files. I set my random seed to 42. because I want you to be able to replicate more or less my results. This step is only necessary if you want to ensure replicability. When we look into experiment tracking, most experiment tracking mechanisms should also be able to track your random seeds, right? So experiment tracking systems are meant to reduce as much as possible any form of variability, and random numbers generators, of course, will induce some variability. Okay, so I do this line random.sample. So random.sample, what it will do is it will sample from a list of objects. So you have a list called my list, and this list will contain the numbers 1, 2, 3, 4, 5. And then I do random.sample my list, comma 3, right? I will randomly sample. Oh, I didn't import the library. My apologies. I know that I didn't import my library because it says the name random is not is not defined. So I haven't set Python understand by random what you usually understand like random. Okay, and I get 432. That's my random sample. If I were to run it over and over and over and over and over and over again, I will always get different results. But if I use something like what I did over here, random seed, okay, I will always get the same result, right? I'm fixing the randomness with that seed. And if you want to understand how these mechanisms work, I highly encourage you to look into Wikipedia. It's a very interesting mechanism. Random numbers in a computer are never random. They're pseudo-random numbers. They look so closely like randomness that we cannot distinguish that they are actually non-random, okay? So let's continue. Then I take a sample of 60 files and I do an empty list. Okay, the empty list is going to be a container. I'm going to use it like a box. Okay, for every file, S file stands for stock file. In stock files, I will first log that I am reading a certain file. Then I will read the file, right? So this part reads the file. Then to the data frame, so this part of my code, pd.readcsv s file, will return a data frame. That data frame, I will modify it, okay? So I will modify it through a pipeline. Now, the pipeline that I will use is it's a very basic and simple pipeline using the assign command, assign method. Assign will assign a new variable, a new column to the entire data set, the entire data frame that from which you are calling it, okay? And basically you do it as variable key value pairs, right? So source is going to be a new variable, and it will contain os.path.basename s file. We discussed yesterday that this is going to be only the file name without the directory path of the file that I'm looking for. Remember that stock files contains both the directory and the file name. So if I do something like os.path.basename of stock files, right? Stock files, no, it needs a string that represents a path. I will get only the file name, right? I needed to do this because basename operates on a single file name, not on a list of file names. But of course, I could do this to whatever file name I have in my list, okay? Now, the other thing that we discussed is this is now a text, right? So I can use another command. So notice how I am linking methods, right? I know what I get, and given that it is a text, a string, I can link a method to replace .csv with nothing. By the way, my code recommendations are coming from Copilot. If it becomes too annoying for you seeing it, let me know. I can turn it off. But I do want you to see what Copilot is recommending. And half the time, I tend to ignore what Copilot is recommending because half the time it doesn't think what I'm trying to do. Okay, so if I run this, I disappear the CSV extension, right? And you can do this with more or less complication. This understands a fair bit of of complicating patterns. I'm not entirely sure if my memory doesn't help me too much today, if it understands regular expressions. And I do want to make a point here. Regular expressions are standard patterns by which we can describe text, right? So I describe a pattern of text and I can test conditions on those patterns. As data scientists, this is probably one of the most useful tools that you can learn. And this is not a standard part of a curriculum of a data scientist. So I'm just going to drop the seed to say, if you are not comfortable yet with regular expressions, I would highly recommend that you look into them. They will save your life many, many, many times. Okay. So we add the file name, we add the ticker name. So the file name without the extension is going to be the ticker, right? So we store it in the variable ticker, and then I do a conversion. Okay. So the conversion is the date. I'm going to transform it using this function, PD to date time, and then I'm going to say date. Okay. What is this thing? This lambda is an anonymous function. Okay. We discussed this yesterday. An anonymous function is function that has no name, as you can imagine. The reason why I write it like this is because of readability. I wouldn't like you to go to another place in my code to figure out that I am trying to reconvert a date. Now, some of you, if you have some experience, may ask, Jesus, why didn't you do something like this, right? I could have done first the read the file. I store it in the data frame called DT. And then to DT, I assign all of this and I call DT again. This would also work and it would do exactly the same thing. I believe that this is a little more difficult to read, but also I would like you to get into the habit of being comfortable using anonymous functions. Anonymous functions will not only work in these very simple type of transformations, they will also help us when we do group by and apply transformations, group by and assign transformations, and so on and so forth. So anonymous functions will be a recurrent theme in the things that we do. In data engineering, they're fairly common, and in general in development, anonymous functions are useful whenever you have situations in which the function itself is not very long, right? Like in this case. Okay. This will run 60 times. I will load 60 different variables. I will modify them, the resulting data frame. And then at the very end, I will append them to the list. Be careful. This is old Python code. This is coming from the 20th century. When you append something to a list, the list is modified in place. It doesn't return anything. If I were to do something like this, if I were a functional programmer, I would be inclined to do something like this. I will get none in my list. This is a super common mistake. Don't do it, right? So whenever you append something to a Python list, it modifies the list in place. I don't need to assign it to something else. So this is good enough. And actually, this is the appropriate way of doing it. So by now, I have a list of data frames. Remember, in Python, lists can hold whatever you want, right? So you can throw things into it, and one of those things are data frames. So we have a list that contains 60 data frames, and by constructions, I know how the files were constructed, and as well, I know what I added to each one of the data frames that I created from each file. I can concatenate them, right? I can stack them one on top of the other. And I do that with the command pd concat. To the concatenation command, I will give it my list, and then I will indicate concatenate them vertically. That is what axis equals to 0 means, okay? I can also have the option to say, hey, concatenate them wide, right? So grow them, but side by side. And that could also be done. I would only change this to 1. Sometimes you want to do something a little more powerful, like a join, right? This will simply concatenate one beside the other, especially if I am ignoring the indexes. Okay, so in this case, I'm going to concatenate using the number 0. This will take about 30 seconds to run. We know that we were going to get all of these messages because the messages we got, and as well, we should be getting a file that has been timestamped with today's date and the current time that contains all of the messages that I have included over here. Now, notice that the calling, the name, right? The underscore name is this weird number. This weird number is the identifier for my Jupyter Notebook kernel, right? If it were, if I were running this under my main, meaning the command line, then I would see here main. And if I were to run it using a module or a class or whatever, I would see it over here. Yep. Very well. No, pause here. Any questions? Yes, Ritu.
Yeah. So the question is, in the code you have replaced .csv with space, right?
With it's not a space. It's actually there's nothing in the middle. It is. I'm replacing it with nothing.
Nothing, right?
Yes.
That means those tnc.csv cv. I mean, the output shouldn't have CSV file, right?
Correct.
I mean, CSV extension.
Yes. There will be one column with CSV, and the next column should not have CSV.
But all of them has it. See the output?
So there's the one column that does have CSV, and then another column that is the same thing without the CSV.
Oh, okay.
Okay. So notice I called this source,
Oh, yeah.
and it is source over here, and then ticker is the one that doesn't have CSV, and that is the one that doesn't have CSV.
Yeah.
Good. Excellent. Saad, please. Yep.
Oh, you can hear me. Okay. I understand the convenience part of using the log function, but what would you say the impact is in the real world, or the impact like application of log?
Of these logs?
Yeah, like keeping a
Wherever.
log file.
Oh, yeah, no, it's super important. We're going to run heavy processes, and some of these processes can run for hours. So when things run for hours, and especially if you're running them remotely, right? So you have a VM or you have a container or something that is running somewhere else, most of the time you let them run and you go away, you disconnect and you go home and so on and so forth. So if the process crashes, the logs are the only mechanism by which you can inspect what happened. That is the most practical application I can see. Now, if you want to do something a little more complex, you can hire a service like Sentry, for example. Sentry will analyze your logs, and whenever it detects error, so instead of here having info, you have something like error, like this. Notice that even VS Code just automatically color codes it. A system such as Sentry will send you an email saying, hey, I am looking at your logs and your logs say that something went wrong. Take a look at it, right? And you can configure it, right? So you can have a reporting system that says, whenever I see a warning, an error, et cetera, send me an email, send me a Slack, send me a text, that sort of stuff. So it is. And I think in most shops, at some point, some senior dev will tell you, log your things, don't print them out to the screen. So yeah.
Okay. Thank you.
Yeah. Sneha, please.
Yeah, hi. So
Hi.
why did you call it a pipeline? The assign command which you used in dt equal to
I am sorry, I didn't.
$10.
I don't understand. Why did you call it what? I'm sorry.
A pipeline. You
A pipeline.
mentioned
Yes,
it
yes,
as
yes.
a pipeline, right?
It's a pipeline because there is a sequence of operations. Okay, so the first operation is this one, right? And it creates a data frame. A data frame that looks like this data frame, but without these two columns. Okay, and then I add operations to the previous operations, right? So the first operation is read something and create a data frame. The second operation is take that data frame and do things to it, assign new values, right? Transform the data frame. Then I can add more operations on top of it. Group by and aggregate the data frame. And then I can add another one, save to a CSV file. So the concatenation of all of these operations, which are running sequentially, right? So one, and then the second, and then the third. That gives the notion of a pipeline, the sequencing of it. Okay, make sense?
And yes. And
Brilliant.
what if we want to use these sequence of the commands that you used in the pipeline again and again? So, like, is it a way to store the sequence of command in another variable so that we don't have to write it all over
Like
again?
this? Oh, you mean,
Yes,
yeah, like a function, you mean? Yes, you can enclose this in a function if you want. And it's actually a very interesting way of programming. If you're a developer, and I don't want to overcomplicate things too much, there are many paradigms in developing your code, right? So there's object-oriented programming, but there's also something called functional programming, in which you don't change the state of your objects. Let me be very clear here. If you have a data frame under the paradigm of functional programming, you should not be modifying that data frame. You should create a new one. And what you're saying, Sneha, would imply you create a function, right? All of the transformations, you pour in a data frame on one side and you create another one on the other side. And that way you can reutilize that function over and over and over again, right? And if in addition to that, you make it so that you do not overwrite the original data frame, so you create a new one, then you can parallelize that operation. And that is very powerful. When you progress in your career and you face Spark, you will need to code this way because Spark requires you to do functional programming. Okay.
And with regards to the assign function, you said that it will create new columns in the existing data frame. But I saw that you also wrote data, the column data, right? But it was like existing data, not the new one. So it also like
modifies existing columns. So if it exists, it overwrites. If it doesn't exist, it creates a new column. Yes, that is the right way of doing it. Sat?
Thank you.
No questions. Thank you.
Brilliant. Okay, so we covered all of this. Lastly, we said we want to inspect stock prices, right? So a quick and dirty way to actually inspect stock prices is by using the function, the procedure info, and it will give me view of the schema within the data frame. Now, data frames are a combination of NumPy and the things that Panda adds. Okay, so NumPy is a very powerful vector library, right? So it allows you to do vector operations, meaning you can multiply dot product type of operations, right? So to take one vector, multiply them element-wise, add all of the results, that sort of stuff. You can invert matrices and so on and so forth. So with these operations, you can actually create a number of algorithms. And the reason why Pandas has an underlying NumPy implementation is because we want a fast way of performing these operations. There are a few caveats. NumPy is going away. Starting in Pandas 3, NumPy will no longer be the underbelly of Pandas, and it will change to PyArrow. And all of these things will change. So in the near future, by the time you graduate, most likely when you install Pandas, you will see something different over here. Pandas will become faster because of this change. And it will be natural for Pandas to start working with objects like Parquet files. Okay, so it's a very exciting change. It is something that a lot of people have proposed. There's a competing library. And I think that part of the reason why Pandas is changing this way is because of the competition. And the competing library is called Polars. Polars is an equivalent of Pandas. And it does exist in the underbelly, the underlying library is called, oh, sorry, I do not recall the name, but it is written in Rust, a very highly compliant and fast programming language. So Polars is also very popular. It's becoming very popular, and it's also quite fast. When you decide, and you will need to decide what to learn, there's too many things to learn. And so you need to be selective of what to learn. You need to be mindful that there will always be hype, and your time is limited. If you pursue hype all of the time, you will probably learn very little, right? Because things are coming out so fast that you won't have time to actually absorb everything. So be mindful of what you learn and how you learn it. Explore, ask around, look at the surveys, and see which libraries are more popular than others, such that you can inform yourself and actually increase your employability. Okay, so Polars is a competition, Pandas is changing, and there was one last thing that I wanted to mention. NumPy is column oriented data frame. So it's written column by column, whereas Pandas is row wise oriented, right? So it's row major. There is a certain cost implied in this conversion. So use Pandas for small data frames, right? There are better ways of working with larger data frames, and we're going to see a little today. Okay. Now, we may want to do a bit of an exploration. I want to compare Parquet versus CSV. The first thing that I'm going to do is I'm going to show you the tickers that I selected. So if you remember, I selected 60 tickers. These are the 60 tickers that we selected. We selected them randomly. There's really no reason why we selected them. They come from different parts of the US market. Now, this function, I'm not going to walk you through it. It's just a function that does what its name says it does. It gets the size of the directory. There's really nothing much other than it scans a dir if it finds a directory. If it finds another directory, it explores it. If it finds a file, it calculates its size, and then that's basically it. The one complicating factor, or perhaps the two complicating factors, is one, I am using recursion. This is not a programming language, but notice that this function is calling itself. Okay, so that is a pattern that is called recursion, and the main thing to remember is that there needs to be a exit condition. If you call the function is calling itself over and over and over again, and there is no exit condition, we will always cycle through the process, right? So the exit condition over here is if I find a file, then calculate its size. The other trick that I did is this plus equal sign that I'm using here. Okay, plus equal means whatever the total variable contains, add whatever the thing over here is, right? So it's just a short form. This could have been total equals total plus entry.stat and so on and so forth. Okay. So if I run this code, nothing will happen because I only define a function, right? So I define the function that gets the size of a directory. I'm going to load a couple of more libraries. I need the time library to measure elapsed time, and this shutil shell util function to I don't even recall why I run it, but I run it for this. Yeah, because I may want to clear out a few files. So shutil.rm3 remove tree will delete files. So be careful around this code. Okay, so I get the temporary directory. I store it in temp. I will save a file, a certain file name with CSV. CSV dir inside of temp. I will remove whatever it used to have because I may have run this code many times. And then I will create a file path. So I'm using the same function, os path join, whatever directory I have created. It's just a path in a temporary directory and a name. This is just my name, right? And I will take my sample of 60 stocks and all of their prices and push it into a CSV in there, right? This function, os make dirs, is a very friendly function. Many times in Python, when you want to write a file, it will first check if the directory exists. If it doesn't exist and you try to write the file, you will get an error, right? So this function, what it does is it checks if the directory exists. And if you add this parameter, exists OK equals true, if it exists, nothing happens. And if it doesn't exist, it will create it. And if your path has a directory, a subdirectory to how many levels you want, it will create the entire set of directories automatically for you. Okay, so it's a very useful function. It is something that you probably will use over and over and over again, because it just makes it very easy to create directories. Okay, so there's nothing here. Actually, I can show you what it does. This directory temp, I can delete it. Okay, and I run my code again, and it created the temp directory and the CSV directory inside it. Okay, that's the only thing it did. Finally, I'm going to start a timer. I'm going to write my file to a CSV, and I'm going to end my timer. And then I'm going to print out and log my results. I'm going to say writing the data, right, a certain shape of data that I have to a CSV, took a certain amount of time expressed in seconds, and then I'm going to call my sizing function and see how many megabytes it has taken. Okay. So I'm going to wait because this is CSV, and I wrote almost 240,000 rows of data across 9 columns, and it took 5 seconds and consumed 26.6 megabytes. Okay, so that is my comparison point. I have written a CSV file. It took 26 megs, and it took about 5 seconds to write. Now I am going to call a library, Dask. So pandas, Dask. Okay. When we have small data, we use pandas. When we have medium-sized data, we call Dask. Just to give you an example, if you have a modern laptop, probably small data is up to 1 million, maybe a couple of million rows. If you start reaching the 2, 3, maybe 5 million rows, then you may want to start using Dask. Dask does everything that Pandas does, but it does it in parallel. Actually, Dask implements as well certain machine learning libraries and procedures that you can use and to actually run and train your models in parallel. The reason why I want to introduce Dask to you is that it is highly likely that many of you will not need something that is as large as a Databricks cluster or a Spark cluster, which can handle several millions and billions and trillions of data points. Those are massively parallelizable systems that you can rent in the cloud, and they're very fun to use, but they are meant for very large data. If your data set takes, I don't know, 20 gigs, has 20 million records, 50 million records, 100 million records, Dask will help you do it. We run processes. I think there's one that we run every month, and it takes about 60 million records every single run. And it takes a few minutes. We wrote it in Dask. It handles perfectly well. So it is a very nice intermediate solution that doesn't break out the big data tools, and you can still experiment with it in your laptop. The way you do it is you install Dask, for example, for sure, but then I import Dask data frame. Now, notice that I'm not importing the entire library, right? So I'm not import Dask as the same way that I import pandas. Many times you want to do this because if the library is very large, you will be consuming memory that you will not use, right? This is the case for Dask. It's the same case. It's going to be the same case for scikit-learn. Large and complex libraries, you may want to use this approach. Okay. Same story. I will create a Parquet directory called Parquet very creatively. If there was something in there, I will remove it. And if there's nothing, nothing will happen. And then I will actually create a directory. So here I only create the name, and here I create the directory. Here's my temp folder, right? So now I have temp, I have CSV, and Parquet. And I'm going to do the same thing that I did a few minutes ago. Now I'm going to run it with Dask. I'm going to show you that it took much less time, 2.59 seconds against 5.3, right? And it took 9 megabytes as opposed to 26.6. Okay, so it is optimized both on time, on size, and in addition to that, we like Dask because it is column major format. So for as data scientists, I can go into my Dask data frame and say, DD, Dask data frame, dot read parquet, these columns. Okay, so let's see how we do that. Now, we're working with a fair bit of data, right? So we have 240,000 columns, just large enough for it to make a difference, a few seconds. And one of the things that we want to do is to have a strategy on how we want to update our data sets, right? So we know that the market opens every day. There's operations. I can read the new data every day, and I will probably need to store it, right? And this is very common in whatever activity you're doing, right? You're running a supermarket, you're running an airport, you're running a hospital. Every single activity will create data, and we want to acquire it, land it, and attach it to my data frame. The initial impulse is to read everything, including every history, and create a new file. And that is probably not the best way you want to do it. What you want to do is you can create smaller files that are time-stamped, for example. So that it doesn't need to be timed. It just needs to be an ordering variable. But in this case, it's time. And we only read a delta, the most recent delta. Okay, so that delta can be the activities that occurred during the past week, during the past month, during the past day, right? The most recent activities. And what we do is that for every week, every month, every day, depends on what the appropriate time period is for you, we will write a Parquet file. Remember that we cannot modify Parquet files. Once they're written, they're written. If we want to modify them, we need to delete them and write them again. But if they have the same schema, they can also be automatically stacked. And that gives us the opportunity to create a piece of code that will take our data, partition it by time, for example, and then start adding chunks that are time-based. Okay, and that is what I'm going to mimic right now. It was nicer when we had Yahoo Finance, but because then you can run the code every year or whatever, and it would update. But let's mimic what we have. Okay, so here, basically what I'm doing is I get a certain directory from my environment files. Once again, I use the shell utilities library. And if a certain path exists, I will remove it. Okay, and I do this because we are going to run several times the code, and I just want to clear it out to avoid any potential mistakes. The other thing that I do is I can query my data frame. I want to see what my columns are because I will use them here. And in this little piece of code, it's probably not the most efficient piece of code, but I wanted to be clear in my intentions. I will take every single ticker, right? So remember, my data frame has a column that we created called ticker, right? I will calculate the unique values of it, and I will iterate over them. So I will go under ticker A, AB, AC, and so on and so forth. And then for each ticker, I will subset my data frame. Okay, so this is a very simple way of subsetting it. I would assume that you already know what it is, so I'm just going to very quickly go through the logic. This portion over here, so let's say the ticker is going to be equals to A. I think that there's a ticker called A. Yeah, I have a ticker called A. Okay, so if I do something like this, I will get a vector that will have true or false depending if the column ticker is equal to A, right? So ticker is equal to ticker, right? So I can write that this, maybe it becomes a little more clear. I'm going to do a trick. I'm going to assign this to a column index, and then I'm going to sum all of the elements in index, right? In this case, I'm finding that the ticker A is not in my stock prices. So let's see why that is. So let's do stock prices, ticker, unique. Maybe we made a mistake. Okay. And what this will do is it will extract the column tickers, and then I will apply the unique function. And this will give me the values of the ticker. And of course, I forgot to think that I was using a randomly selection of tickers. So I'm going to take now this ticker over here. Okay. So I'm going to do it like that. I need to enclose this into quotes. And now you can see there's true and false. And if I sum this, I can get the count of how many tickers of the form TNC are within my data frame, right? So I know that there are 11,883 rows that have the ticker TNC. Okay, so that is how I subset. But in addition to that, if I enclose this thing like stock prices and then square parentheses like that, I will only get the part of my data frame that contains the ticker equals TNC. This operation is called subsetting. Sometimes you can see it as indexing. I think that's what the pandas documentation say. And it is super common. This is the simplest way of filtering data within pandas. Okay. Now there's nothing stopping us from using other operators, right? It can be less than, greater than, and et cetera, et cetera. It can be different than, and more complicating functions. The only thing that you require is that this thing that happens within the square parentheses is a Boolean variable. It's either true or false, and that is how you can get the sub-indexed version of it. If you want to do something more complicated, there are a couple of methods that are called lock and ilock. Okay, and we may, I think that we actually use them further down in this code. Okay, so we're here. For every ticker, I will subset the ticker data for that specific ticker, and then I will assign a variable called year. I don't need to do it over here. I did it here because I had not done it before, but you can always do it in your silver layer, right, up above. And then I iterate once again. For every year, I will subset, where the year is equal to the current year, and I will create a Dask data frame. Okay, so Dask data frame, I imported it all the way over here. Import Dask.data frame. I generally abbreviate it as DD. And we say, oops, let's create the Dask data frame from a pandas data frame. Okay, so pandas and Dask are highly related, and you can create a Dask data frame out of a pandas data frame, but that is not the only way. You can actually read directly CSVs and Parquets and so on and so forth. The one thing to remember is a Dask data frame is not a pandas data frame. They are not interchangeable. You can convert one to the other, but it is not automatic, and you'll see why in a second. Okay, I create a certain path, and the path is going to be within my price data folder, right? So there will be a price folder. I will add ticker, right? So I'm joining price, whatever the value of ticker is. In this case, it's going to be TNC, and then whatever the year is. And notice that I'm using an F string. An F string in Python basically allows you to create strings using the values of variables. Okay, in this case, I'm going to create a string that has ticker and year in the same within the string, right? So it will be something like TNC underscore 1999, TNC underscore 2000, and so on and so forth. And then finally, I'm going to make a directory with this path, and in there, I'm going to write my yearly data using a Parquet format. Okay, and the underlying engine, it turns out to be PyArrow, which is what Pandas is converting to. Okay, so there's a lot of an ecosystem going on in here. Okay, so I'm going to run this this chunk of code, and notice what is happening over here, right? A bunch of Parquet files are appearing, and they probably shouldn't be appearing. No, sorry, this is not the place where I should be doing it. I should be looking over here. So prices, I created a folder, right, with a ticker, and then a subfolder with the ticker underscore the year, and then all of the different Parquet files, right? I write 2 Parquet files per year, and you will see it over and over again. Okay, and wherever you go, there are different years. Not all of the tickers have the same year. So notice here that ALDX started in 2014, and then this one down here, AMH, started 1 year earlier, and they don't also end in the same year. And what I'm doing is I am creating a whole bunch of files. They have all been indexed by the year, and this is just one way out of many that I can create the files. All of the files are Parquet files. All of the files will have a Parquet extension. It's the easiest way to distinguish them, but they don't necessarily need to have a meaningful name. You can give it a meaningful name if you want. Now, Parquet files come from the Hadoop environment, right? And in Hadoop, there's a weird way of understanding directories. Directories don't really exist. Directories are just file names, right? But it is very easy for us to consider directories as containers, as meaningful containers. So fundamentally, what I'm doing is I am creating a namespace. I am organizing my data in such a way that I know where I put things, but the names don't really matter. I could have used the same directory and just dumped all of my files in there, and that's it. However, if I did that, my data lake most likely will become a data swamp very easily, right? Because I'm creating data and data and data, and tickers change every day, and I'm just adding more data. And if I don't keep good order, it will be very difficult for me to actually go back and understand where I put things. Okay. Now, let's read it, right? We know this trick. We have used glob before, right? So I know that I can use the glob command to extract all of the files, and I just created a huge amount of files. Okay, so what I'm going to do is I'm going to read using this command, right? And now I'm going to use my recursive equals true, and I'm going to get all of the Parquet files that I created. Let me just open this in a text editor so you can see the length of the list that I got. These are the files that I just created in the last minute and a half. Okay. Now, before I continue, I do want to show you that the total size of this directory is really not that large, right? So open terminal, I will calculate here my properties, and I have 2,000 files across 27 megs. Let me compare this with, this is just a subsample size. Okay, but it's 27 megs against all of these files that we have just created. I took a wrong turn. Okay, so now what do we do with these things? These things will be stored in my object called Parquet files. Once again, these are only the file names. And I'm going to take this list of 2,000 and something files and just give it to my function read Parquet. Okay, and it will read all of the Parquet files in a single sitting. Okay, it's done. I've read everything, 2,000 files. Let's see what they contain. Okay, you put it here, and I stored them in dd_px. Okay, if I do that in pandas, typically I would get a view at the very least of the first few rows of my data frame. Right now, what Parquet is doing, and just because of the first time that I run it, it's going through all of the files and verifying that it has the same schema. And it will not display the 260 something rows that it contains. It will display a skeleton with the structure of my data frame. Dask does not perform any operation that is data intensive unless it is explicitly instructed to do so. Okay, and the reason for it is meant to work with very large data, right? The only thing that it did is it estimated if the operation can be completed without any error, and if it cannot complete without errors, it will indicate it to me. Okay, but I cannot see what the contents are. And then you will ask, so why are we here, right? Why are we using this? The response to that question is we will create transformations, we will add things to it, and we will make sure that it runs. And then at the very end, we will say, hey, compute, right? And we will go for coffee. And when we return, the computation will be done. Okay. So we're saving the most time-consuming part of the process, which is the execution to the very end. And Dask will allow us to design our pipelines, make sure that they work, and then we will execute. This paradigm is called lazy execution, and it is not exclusive to Dask. This is something very common in big data type of applications, right? We don't want to run and just wait 3 hours for something to complete and then realize that it's not what we wanted. Okay. Now, I will transform some of the data. Okay, I'm going to start with my price data, and I'm going to apply a group by operation. Okay, so group by ticker, and then I will apply an anonymous function. Okay, this anonymous function, what it will do is it will assign. Remember, we're assigning a new variable called close lag 1. So this is the closing price lagged by 1 day, right? So I want to get the previous day closing price. Okay, so I do lambda of x. I'll define close lag 1, and then I will take the column called close and apply a shift of 1. I note that they are ordered by date, so a shift of 1 will give me the previous date. Now, there's one big thing over here. I am using a group by operator. Okay, the group by operator is meant to the group by operator is meant to group the operation by ticker, right? If I were to perform just a simple shift operation on the standard data frame, when one ticker changes to another ticker, that shift will contaminate the data, right? So I will be traversing a barrier that I don't want to traverse. If I have the ticker A and then the ticker B, I don't want a price of the ticker B to become part of the record of ticker A. So instead, what I do is I group by my data frame, I group it by ticker, and then I operate for each group. And that is where the real power of the Lambda function comes in, right? Because this X is no longer the entire data frame. It is only the group that I am operating in. Okay? Was that clear? I want to make a pause here. Yes, Tala.
Does the group by do the sorting as well? Because in lag we need sorting, so it knows which records to go.
Right. No, it does not. This is by construction. This is by the way that the files were read, and I know that they will end up in order. But if you need to add a sorting operation, my recommendation is to do it once and do it at the beginning. Okay? You sort your entire data frame. It's a super expensive operation. And actually, after you sort your first data frame, that is an appropriate time to actually save it because it will take time. Right. But right now, given the way that we have downloaded the data and we created the data frames, that is how I can guarantee to you that this data frame is sorted. But that's it's a brilliant question. Thank you. Tejinder.
So this group by function would be on row level, right?
It is a group by on row level. Yes.
So yeah, please continue.
Oh, no, I was going to say, generally in Pandas, and sorry, in Python, most libraries, I may be mistaken, but most of what I have seen is, and in R as well, rows indicate observations and columns indicate variables. There are certain systems, I believe, in genetics and areas that I'm not very familiar with that kind of like take the other approach, in which variables are rows and then observations are columns. But I haven't seen it as like a standard widely used library. I may be mistaken, but yes, what you say is true.
So wouldn't Dask would have a problem with while working on this one? Because I guess you mentioned that it is a more of a column when we are making operations on column, it comes handy at that time.
Ah, I see what you mean. So the way it would operate is it takes the column ticker, right?
Mhm.
Parallelizes the computation of groups, right? So it takes portions of the data frame and partitions it and sends it to different cores in your processor. So your processor has, I don't know, 12 cores. Dask will take chunks of the data and send it to different cores. And then within that, it will define the groups. It will find in that variables where the groups are. Then it will report back to the overall procedure. It will put the results together, and that will become an index. And then the operation, the apply operation, will operate on those groups defined by the first task. I
So
hope
it
that
yeah
makes sense.
this would be possible on each and every row level operations, right? I mean, there wouldn't be any limitations on the operations. So why we are saying that it is it can do that division kind of thing on any.
A column major. You mean, is that where you're going?
Yeah.
Okay, we don't need to read everything. We're only reading two things, ticker and close. That's it,
Hmm.
right?
So is it possible? Sorry, it's
No,
good.
and that is the reason, right? Because right now we only have 9 columns, but if we had 90, then it becomes an issue, right?
Okay, makes sense. So
Makes
is it
sense?
possible to use uh, uh pandas and Dask side by side? I
Yes.
mean, for some operations we can use pandas, for some other we can depend upon our use cases and the library, right?
Yes, actually, there's and it's a good thing that you bring it up right now. I'm gonna take like 5 more minutes, and then I'm gonna address that use case where you say, when should I use pandas and where should I use Dask? And but I need to complete the discussion before I jump into that. Okay, so
Sure. Thank you.
patience.
Yeah, please.
Excellent. So a couple of more things. Apply. We haven't seen apply just yet. The difference between assign and apply is as follows. Assign will take something that looks like a data frame and modify it. Okay, it will either add a column, or if the column exists, it will modify it. Apply, on the other hand, will return an entire data frame, right? So what I'm doing here is I'm saying, hey, take my large data frame, group it, and then to each group, apply this operation. The operation is take the sub data frame, right? Do something to it and return the data frame, right? The data frame that is returned then is stacked one on top of the other, and it will be indexed by ticker. If I don't add this modifier, I will get a new column called ticker. And I don't want that. I don't want repeated columns. That's the only reason why I add this false group keys equals false statement. Now, this thing that I got here is not an error. Okay. The reason why I know it's not an error, several fold. The first thing is it doesn't say error. It says warning. Okay. This thing also indicates that my code completed, right? So it ran, it didn't fail. When you see something like this, Python is telling you, hey, something might be wrong, something may not be entirely right. Pay attention to this. And what this specific warning is telling me is that I did not provide a schema to a resulting data frame. And what Dask will try to do is it will try to infer a schema from a first few rows of calculations. If I want to shave a bit of time in this computation, I can always add a meta parameter, a meta input, and define the resulting schema that I am expecting. That is entirely possible. This is what this thing says. Okay. Now, the other thing I want you to notice is I didn't override my previous data frame. I created a new one, right? These names, I choose them on purpose, and when I work in Dask, I like to keep my names unique. I try to follow this functional paradigm that I was telling you about. It just keeps it cleaner, and you can get better order. And given that you are doing lazy execution, you are not consuming a huge amount of memory, right? These are just objects that store parts of the pipeline, right? That's what we're doing. We actually can create the pipeline just concatenating using the dot operator over and over and over again. Okay, so the final thing that I'm going to do is I'm going to calculate returns, right? In the previous step, what I did is I just shifted the price. So I obtained yesterday price. So now every row will contain, actually, I don't need to move my hand, so I can just display it, right? Now every row will contain an additional column called close lag, right? And this is the previous day's closing price because I want to create a return, okay? So this is the return. And the return, once again, it's just very simple, right? It's the closing price for today divided by the closing price of yesterday minus 1. Standard definition of return. By now, I would have liked to see my my computations, but my computations are not done until I actually tell Dask compute or save, right? So if I say compute or I say something like to CSV, then it will actually perform the computation. So let me just run it, and it will take a bit of time. A bit of time is really not that much. The one thing that I want to highlight is Dask is a very powerful library, and once you start moving away from Python, you can actually make use of a lot of its capabilities. It is such the capabilities extend with beyond your laptop. As I said, you can parallelize within your laptop and send different operations to different cores in your processor, or you can send it to different machines. Like you can start thinking that this is like a mini Spark or a mini Databricks. So it's a very nice library. If you know where to start, Dask is a good place to start. This is the result. Of course, the first row doesn't contain anything because there's nothing to lag, right? So we don't know what yesterday was for the first date, right? But every other date, we have the previous day's closing price over here, and then I have created the return. This stock on this date, July 20th of 2021, ACN lost 1 point something percent. Okay. And I did this for my 240,000 rows in a parallelized form in 27 seconds. Okay, that is Dask. Now, I said, well, before I say anything else, I want to run it. Sorry, I want to save it, right? So I just get my features data, I run this thing, and this thing will create a features folder in my 05. So let me just make it easier for us to read. And in this features folder is where I will start seeing a number of Parquet files appearing. Now, Parquet files are, if you don't do anything to it, they're generally created with a partition embedded in it, right? And the partition is generally indexed with one meaningful variable, ticker, for example, but it could be a date, or it could be something else that is meaningful for the data set. I can define it. I didn't define it in this case, and it will just use a standard partition. In this case, I had a partition of 60 files, and that's the reason why you see 60 Parquet files. So it starts counting in number 0 and it goes all the way to 59. And each one of these Parquet files will have the same schema, and they will be able to be stacked together. Okay. Now, I will use my last 4 minutes to walk you through what this thing does, right? So from this moment on, if you are interested in doing this in Python, I would do it like this. Okay, so this is for your homework. Sorry, before I move on. Everything in this notebook you will use for your homework. Everything that I will discuss from this moment on is just basically for your knowledge. Okay, so now this file over here will generate a similar data set. I have created a class. Okay, the class is called Data Manager, right? Why? Because I'm managing data. There's really no other reason. When you talk about object-oriented programming, you will come across this concept of class. And there's a whole philosophy that classes of objects are reflections of reality and so on and so forth. For all practical purposes, a class is a thing that will hold data and functions together. Okay? Think of it like that, right? So this class, Data Manager, will have certain variables embedded in it that will hold data and certain functions that will be linked to the data. And this is a very convenient way of working because when I have a class, I know that everything that the class needs is in there or it is called and it's in the initialization procedure, right? That is the way I like to write my classes. That is probably the way that you will be asked to write your classes. The reason I do it this way is because I want to keep the function footprint as small as possible. Notice that all of my functions have very little, by the way of a footprint, right, of the parameters that it takes. And that is in general a good coding practice. The other thing that I want to do, and I strive to do it, is to write as small or slim functions as possible. Every function should do one thing and one thing only, right? If I'm able to keep to these two principles, write functions that have a very slim footprint and a very slim code within, you will tend to write very clear code. Now, this is an aspiration, right? You can always do it better. And of course, every time that you look at your code, you clean it up, you reformat it, and so on and so forth. Okay. The one exception, of course, is the constructor function. So this initializes my object, right? So a class is an abstract object. When I make it concrete is because now I am specifically talking about something that has a name, a location, a path, a file, that specific case. It stops being abstract. Okay. Now in this case, I'm going to take a CSV directory, a price directory, features path, tickers files, the number of samples that I want to take, a random state if I'm interested in, and I save it into these things that I call self. Self means my own self, right? So self in this case is the data manager, right? And I save them, right? Whenever I need them. So in this case, for example, I say, hey, process all files, and I call this method get file list. Notice that everything is self something or join the path that is in price CSV with something else, right? So self means look into yourself, right, class, and look into what data you have, and that is where you will find it. And the same thing goes for the functions, right? The functions are not stored in the ether, they are stored in its own self. So the first thing is self dot whatever whenever you are inside the class and you want to call its own data and its own methods. Second thing is I have functions that call other functions. And this is just to give you good order, right? So if I want to process all files, I get the file list and then I get the data in save by year, right? So what happens in get files list? I right click and really nothing, right? So I just do a glob and it will give me a list of files and I save it to myself. And then from that file list, I go and get the data, right? So I get stock prices and then I save by year. Now I'm using something weird here. Instead of using self, I am using data manager. I purposely did this as a static method. A static method within a class means I won't use the data inside the class. The reason why I want to do this is I want to be very careful that I don't modify any data inside this function. And I am forcing myself to do so, right? I'm modify it and I need to return something else. Something else can be something that I return to the caller or something that I write to my drive. Okay, and that is what I'm doing here. The code itself is exactly the same code that we have just discussed. So when I say I write my code, I draft my code in Jupyter Notebooks, and then I transfer it to a Python code, this is exactly what I mean. Okay. The last bit, because I know we all want to go on a break, is if name equals main. Okay, if name equals main means if I am calling this from a command line interface, my name will be name. Okay, and I can add this very convenient. Let me just make this a little farther away. This is an interface to create a command line interface. Okay, ArcParse is a standard Python library that will allow me to create a very nice command line interface. So let me just give you an example. I'm going to change my directory to 05 source. Okay, and then I'm going to say Python, what was this? Stock prices, I think. Yeah, stock prices -m. Okay, so important to add -m stock underscore prices dot data manager --help. Okay, so what this will do is it will call within the stock prices folder, the stock prices folder, the module called data manager, and from it, it will see if there is a command line interface. And there is, right? And this ArcParse module automatically gives me a help that comes over here. And I can run my data manager by simply doing something like this. Maybe I want a number of samples equals to 3. I don't want to take too long. And I want a random state equals to 42. Okay. And I run it, and it will perform all of the operations. It will log. I'm no longer using Jupyter Notebook. My logs will appear in the same place. All of my environment variables are being taken from my environment file. And this now works as a standalone thing. I can take this code and push it into a server. I no longer need my Jupyter Notebook. Gonna pause here, see if there's any questions. Divita.
The M flag do?
Okay, that's a great question. So the M flag means module. We are going to run my code as if it, understanding that it is a module within Python. So I'm not running a .py file. I am running something that is meant to be imported as a module, right? And that is what the M flag does. Notice as well that I didn't use the .py extension in my running, right? And that is just a stylistic thing. I think that this thing should work also without a -m, but I would need to add .py over here. But I encourage you to use the -m. Okay?
Yes, thank you.
Rita.
Yeah, so we haven't run .py file before. Just trying to understand how you run it. Like this is one way of running .py file, and there is one run button on the right hand side on top, right? That the top right side.
Let's go here.
Right. Yes. That way also you could run it, right?
I have no idea, to be honest with you. I typically write my code so that machines can run it, not so that people can run it. But you're right. I don't know. Let me click. To be honest with you, I need to try it. I haven't even noticed that there's a play button over there. So I apologize. I have no idea. So,
I tried it myself, and then the output goes to the log folder.
oh, okay. Interesting. I once again, I am sorry. I don't think I can answer your question, but I will investigate. Thank you very much for bringing it up, and then I'll come back to you with how it works. But thank you.
No problem. Then now, when you are running it through PowerShell, you are passing some data while running it.
Only parameters, right? Only the
Okay.
parameters, the number of samples that I want to create in the random state, right? And because of that, I mean, you can follow the code over here and see all of the different things that I can do. Also, these messages that I left are the messages that appear in the help response, right? So what I'm doing is I'm creating a tool that contains the help file within, right? The entire thing is self-contained. And that is a very desirable function, right? That is the way that we want to do it.
Okay.
Okay, makes sense?
Yeah, sure.
Brilliant. Any other questions? No? Let's take a 10-minute break. I'll see you guys in 10 minutes. Thank you so much. Excellent. So let's move on now to the training part of our course. Okay, so let me share my screen. Screen share. Okay. Brilliant. Okay, so as always, let's look at our map. Okay, our map indicates that we have gone through data engineering. We know how to use Dask. We can do a couple of transformations. For your homework, you will need to do a couple of transformations, read in some data, play around with the tool, basically. There are a lot of transformations that you can work with, Dask, Pandas, and so on and so forth. If you are in the business of being a data engineer or are creating warehouses and that sort of stuff, I'm sure that some of these procedures are going to be useful. A lot of the time that you will be spending in data engineering is actually optimizing your pipeline such that they are robust, that they can be tested, that they can be deployed easily, um, and um, and that they don't take forever to run, right? Sometimes these operations take a very long time. So it's always convenient to do a bit of optimization. Now we're going to pass to the next stage. And that is, we are going to start developing a model. And developing a model will require us to first featureize, create features. Then select a model, try those features with different models. And once we have more or less a good idea of where we want to go, we will optimize each one of these models. And for that, we will need to use a bit of a heavier machinery. The main idea that I want to transmit to you today is that feature engineering is a necessary step in most machine learning projects. A few years ago, there was this network architecture called deep learning, or not network architecture, but a few procedures that were used to create deep learners, which are neural nets that contain several stacks of hidden net neurons. And for those of you who are familiar with the subject, the idea was that using a sufficiently complicated model, or complex model rather, we can do away without any feature engineering, right? So that means that we could just throw in some data, and the model was complex enough and flexible enough to provide us with good predictions, regardless of what the data is. And the practical answer to that statement is not really, right? Feature engineering is the part of the process by which we convert our features using some functional transformations um, into new features, into new variables that bring out the information content of the original variables in such a way that our model can use it. Let me give you a bit of an example. Linear regression models, they benefit from having normally distributed features. This is just because of the way that they were designed, the way that they were constructed, and many times we may see variables that are not bell-shaped, right? The distribution doesn't have a bell shape. In those cases, we may have kind of like a skewed distribution to one side or to the other, and we want to apply a transformation, something like the Box-Cox transformation or the Leong-Johnson transformation, to bring that distribution back to normality, or something that resembles the normal distribution. If we do that, and instead of using the original variable, we use a transformed variable, we may see that we get better results. What is better? Meaning we get a performance increase in the prediction results that we obtain from the linear model. Other models may benefit from using not categorical variables, right? So if we have a category of variables and we say mammal, bird, reptile, and so on and so forth, some models cannot work with that. Linear regression models, logistic regression models cannot work with categorical variables. We will need to transform them into numerical variables through one-hot encoding or dummy variable encoding, right? And those transformations are feature transformations. Now, sometimes we will see models that are sensitive to the scale of the features, right? If we have a certain feature that is expressed in millions of dollars, for example. And then we have another feature that is expressed in percentage points, a rate, for example, an interest rate. The variable that is expressed in millions may take greater relevance in the classifier than the variable that has a smaller scale. And most of the time, we want to make them the same size, right? And we use a scaling function to do that. The scaling function is basically reducing the mean and dividing by the standard deviation, but both the mean and the standard deviation are dependent on a larger sample, right? So for every observation, we will take the observation's value, subtract the mean, and divide by the standard deviation of the value. So let's say we have a money amount, right, a notional amount in the millions, and we take away the mean and divide by the standard deviation, and then everything will tend to collapse into a variable that has a mean equal to 0 and a standard deviation equal to 1. Okay, it's a very nice feature. Now, the problem is when we calculate the mean and the standard deviation, we're using a sample. And we started our discussion by saying we want to take great care that we don't combine information coming from the training set and information coming from the testing and or validation sets. If information from the validation set seeps into the training set, we will end up learning something that we shouldn't have learned. And the reason or the reasoning behind this is if we have already seen an example, right, we are kind of invalidating this notion that machine learning methods need to perform well on an out of sample basis. So we would be kidding ourselves when we measure performance if our training set is contaminated by the validation set or the testing set, and we will be misled by those results. So whenever we perform feature transformations that require a sample, we need to be very careful that we are not combining the training set with the validation set and testing set. So we will see how to ensure this. Okay, so we're going to discuss this part of the process. Let's start. The first thing that we need to discuss is sampling. Right? Sampling is embedded across machine learning lifecycle. We will need to sample for exploring data, for training, validation, test splits. Sampling is wherever we go. Okay. Sometimes sampling is necessary because we cannot access the entirety of data in the real world. Maybe we have too much data. Maybe we cannot or don't want to use all data, right? So if we are examining trending topics in a social network, we don't want to study the entire history of trending topics since the inception of these services. We may want to see only a sample of the last few hours or perhaps the last couple of days, but not the entire history of Twitter or Facebook and so on and so forth. Okay. Sometimes we want to accomplish a task faster and cheaper, so we need an information that that is important for us to make decisions, and maybe we have 200 million rows of data, and we need to calculate a mean, right? So we can take a sample, a sufficiently large sample, but not the 200 million rows of data. And on that sample, we calculate the mean, right? Why? Because we need to have an idea of distributional characteristics and see before we actually operate on the entire data set if our calculations make sense. Okay, so sampling is embedded in there. Now, there's two types of sampling. We either have non-probability sampling or random sampling. Okay, so let's discuss them. Non-probability sampling. You will encounter this wherever you go. I'm sure you have already encountered this. So non-probability sampling generally implies that we are not random sampling. We have a criteria to choose our sample, but that criteria does not involve randomness. Sometimes it is because of convenience. We sample this data because it is there, right? It is easy to acquire, and we don't need to expend a lot of effort, money, resources to actually acquire that data, right? So this is fast, it's inexpensive, it's practical, but it's not necessarily representative, right? It's not a very scientific way of sampling, and it doesn't offer any guarantees, right? The fact that it's just there, it just means that it's there. I did my BAs in applied math and economics, And there's an old joke that there's an economist looking for his keys in the parking lot, and he's just kind of like underneath a street lamp, and he's saying, "Hey, I'm looking for my keys." Another economist approaches him, and he says, "Hey, what you're doing? Looking for my keys. And where did they fell? Where did you hear them? Oh, I heard them over there." And the other economist said, "Why are you looking over here?" And the answer is because there's light over here. That is convenience sampling, right? So it doesn't serve any purposes. We just look wherever it's easier for us to look. That's it. Okay. Snowball sampling is a bit different. Snowball sampling has to do with exploring networks. And the way it works is you choose a node and you see the other nodes that are connected by edges to that original node. Okay. And once you do that, you look into the connected nodes and perform exactly the same mechanism, right? So you look at all of the edges that are connected to those other nodes and then expand the sample. So the sample starts with one or a few nodes, right? And then you start growing it, and it grows like a snowball. This is a very convenient way of extracting data, especially if we want to trace relationships of nodes that are of our interest. This, you may recall in the early days of COVID, if you unfortunately contracted COVID, you would get a call. And that call was basically to trace all of the people that you were in contact with. That is the precise definition of snowball sampling, right? So you know that you contracted COVID, and um, and because of that, we will perform snowball sampling based on you, right? So who were you in contact with? Oh, my family members. I went out with a friend, and so on and so forth. And then they are called. Who were you in contact with? Oh, I was in contact with such and such and such, and those samples grow. Okay. It's fairly common in social network analysis, and as I said, kind of epidemiology and that sort of stuff, as well as in investigations. If you're in the financial field, or if you're working for the police, or security type of activities, um, you may want to follow suspects, right? And the suspects are people connected among themselves. So that is another potential application of snowball sampling. Judgment sampling. This is super common in finance, right? So in audit, for example, it is common to say we are going to perform risk-based sampling. And risk-based sampling many times is not based on an actual risk measure, but rather it is based on the knowledge of an expert, right? So an expert says, I am an expert in counterparty credit risk. I believe that those and those and those people are very risky. So let's sample them to examine their records and their documents and contracts and so on and so forth. Okay. Sometimes it works, sometimes it doesn't. It depends on your on the acuity of your acuteness of your expert, right? But as again, it doesn't come with any guarantees. There's no guarantees that it is representative of the entire population. And many times you actually don't want it to be representative of the entire population, right? So you want the riskier samples, and they tend to be few and far between. Quota sampling. So select samples based on predefined and heuristic quotas. Select 50 men, 50 women, right? Select 50 boys, 50 girls, 50 plants and 50 animals, that sort of stuff, right? Why? Because I like the number 50, and you add them up and you get 100, and it's just easy to make calculations. Another example, you take 100 samples, equally uniformly distributed across age groups, maybe 10 people between the ages of 20 and 30, 10 between 30 and 40, and so on and so forth. It doesn't matter what the actual distribution of ages in the population is. You said, I want 10, 10, 10, 10, and 10 until you reach 100, and that's it. So non-probability sampling, I guess the only one that I find useful is snowball sampling, because it is a very convenient way of exploring a network, and sometimes you don't have another option. Convenient sampling, not great. Judgment sampling, you will encounter it in your professional practices. Sometimes it works, sometimes it doesn't. It's a hit and miss type of approach. And quota sampling is really not very scientific, so you probably also want to avoid it. So now let's talk about random sampling. Simple random sampling doesn't have much thought to it, right? So every single point in the population is equally probable to be selected as a sample. It is very easy to implement, but we lose distributional characteristics of the things that we care about. And most importantly, we are in a machine learning world, and therefore, the most important thing that we care about is our target variable, right? That is the thing that we want to predict. So usually our target variable will have a certain distribution. Will it rain or will it not rain? Let's assume that we're trying to solve that problem. And we can take a look at the history of weather, right, for the past 10 years or whatever, and know what proportion of days it has rained and has not, right? So when I take a sample, maybe I want to keep in mind the proportion of days where it has rained and not, right? So my sample represents the conditions that I will face in a production setting, in the real world. Okay. What I have just described is called stratified sampling, right? So each class defines a group of observations, and each group of observations is called a strata. Therefore, the name is called stratified sampling. And the idea is that we can take the population and divide it in groups, and then within each group, I will random sample. Okay, and that, as a consequence, will retain the original distribution of elements in the groups, right? So, in the case of the rain, let's assume that 30% of the days rained and 70% of the days didn't rain. And so what we do is we group all of the rainy days on one side, all of the non-rainy days on the other side, and we take, let's say we want to take a 10% sample. We sample 10% of the subset on one side, 10% on the other, and the resulting sample will contain 30% of rainy days, 70% of non-rainy days. Okay, and that is more or less what stratified sampling is. The advantage is that you retain the distribution of groups in the population, right? And it's particularly important for selecting training, validation, and test sets. That is the defining characteristic of our split in training, validation, and test sets. So whenever you run the scikit-learn function, split train, test train, train test split, fundamentally what it is doing is stratified sampling based on our target variable. Okay. Weighted sampling. Each sample is given a weight determined by the probability of being selected. It allows us to embed our domain expertise in the sampling mechanism, right? So it's a little more than just applying expert judgment. So let's assume that we have a situation in which we know the actual distribution in the world, right? So, for example, I know that in the world there will be more or less 50% biological men and 50% biological women, and I'm conducting a healthcare study. I want to see the effects of a particular drug in the body of people, and I want to ensure that I have equal representation of what I know because of general knowledge, that is the distribution of men and women. Now, for whatever reason, I contract an agency and they say, yes, I can get you 100 test individuals. And it turns out that they gave, they selected 70% men, 30% of women, right? So in that case, what I can do is I can underweight my the sample, the part of the sample that is men, and overweight the part of the sample that is women, and then resample from those individuals, aiming to get a 50-50 split. Okay. And yes, the answer is Ruby is yes to your question. Okay. So that is called weighted sampling. Okay. Now let's talk about reservoir sampling. We have a different setting. Now we are in the streaming data part of the world. So we are now no longer in the physical world, we're in the digital world, and we have streams and streams of data, right? So we have trending topics, right? Or even just words, right? A text that is flowing through the Twitter feed or Blue Sky, whatever you like. How do we take a sample on data that is constantly streaming, right? That is a difficult proposition, right? I don't have something like a universe because I take a picture right now and the picture has changed immediately after. So one thing that we can do is we can create something like a reservoir. I think I need 1,000 samples. Okay, perfect. So I create a box that will contain 1,000 samples. I open the gate and the stream starts flowing, right? I take the first 1,000 observations and I put it in the box. And then what I can do is I put the first 100 elements in the reservoir, and then for each element after the 100th element, I generate a random number, right? Such that that random number is it's above or below a certain threshold. And the threshold is determined, and I forgot how it is determined. For each incoming element, generate a random number so that it's between 1 and n, when n is 100. So therefore, I set up a threshold. The threshold will determine if I replace a sample or not. So it is kind of like the replacement rate of each one of the samples. Okay, so let me go back to the original example, right? So we have 100. We take the first 100 messages, the first 100 tweets, and then the 101st comes in. I say, generate a random number, right? Is that random number below k, right? If it is, then I take the kth element, I take it out, and I replace it with a new element. And then I continue with the flow. Every single element that I obtain, I perform the same operation, right? So the kth element is, the element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 100, right? And I'm always replacing depending on the value of the random number that I have generated, right? At any point in time, I can stop the process. And at that point in time, that sample that is in my reservoir becomes my actual sample. Okay? So once again, there's a mechanism that is allowing me to store data. I randomly select a number and then I evaluate against the position. If the number is below the position, then I replace it. And if it's not, I keep it like that. And at any point in time, I can stop, perform my calculations, and this sample will be a random sample. Okay, so each incoming nth element has a k divided by n probability of being in the reservoir. Okay. Now let's talk about the labels. So that was sampling. We will need to sample. Stratified sample is going to be the name of your game in classification proceedings. And if you're working in the in the streaming case, you may want to use reservoir sampling. Now, we also need a target variable, and the target variable requires labels. Where do we get these labels? Okay, the first idea is, well, hire people. Ask them to label stuff, right? Hand labels take a lot of work. It is expensive, and it is particularly expensive if you require subject matter expertise. So if you are, for example, in the medical field and you have a bunch of symptoms, you will require a doctor that looks at the symptoms and attaches the label. It is this disease or the person is not sick, right? And hiring a doctor for that is super expensive. Okay, so that's the first thing. The second thing is that the labels may be inconsistent. In cases in which you have human evaluators, it is highly likely that one person will not have the same annotations, the same evaluations than another human. So you need to spend some effort in creating guides to actually make them consistent and or to have an inconsistency resolution mechanism. Okay, and I'll show a couple of examples in a bit. It may also be invasive, right? Sometimes We want samples from data that contains private data, right? Private information. And I cannot just simply hand over a sample with private information and expect that my annotators will will respect that privacy, right? That's not a control. So what do we do, right? Hand labeling is slow. Okay, so there's a couple of things that we can do. The first thing is we may want to have clear guidance on how to label data. So, for example, in this case, I am labeling data to train an algorithm on named entity recognition. Okay, so named entity recognition is the process by which I give my machine learning method a certain text, and the output is an indication of which words are representing a name, right? The name of an entity, right? A person's name, a place name, an organization's name, and so on and so forth. And these things can vary a lot, right? So this is the same phrase given to different annotators. The first annotator found 3 entities, right? The phrase is Darth Sidious, known simply as the Emperor, was Dark Lord of the Sith who reigned over the galaxy as Galactic Emperor of the First Galactic Empire. Perfect. Okay. So this annotator said Darth Sidious is one entity, Dark Lord of the Sith is another entity, and Galactic Emperor of the First Galactic Empire is the third one. But a different person may have said, look, Darth Sidious, sure, I agree. Emperor is an entity. Dark Lord is another entity. Sith is yet another entity. Galactic Emperor, another one, and First Galactic Empire, right? So it split apart the entire set of entities, right? And then there's an intermediate response. You can join some of them, you can split some of them, right? So Darth Sidious, Emperor, Dark Lord of the Sith, and so on and so forth, right? So in this case, Dark Lord of the Sith was joined together, whereas in the previous case, it was kept separate. Okay. How do we fix these type of cases? Well, a potential solution is to have a clear problem definition and a task guidance. Task guidance can be, well, identify the entities that span the longest string of text, right? So that can reduce discrepancies between annotations, or you can say, hey, give me the entities that span the shortest amount of text, right? So that's another extreme. There might be contextual information, right? So identify entities that that signify appropriate entities for the task that we have at hand, right? So if you have additional contextual information, we're speaking about Star Wars and the Star Wars saga, we will use the main characters of the movies, right? So that could be another annotation guide. Okay, what are the alternatives? One alternative are natural labels. Okay, natural labels occur naturally when the system just creates the labels. So, for example, a few minutes ago we were working with returns, right? Those are natural labels. We may want to predict returns, right? We don't need to do a lot of work, right? We calculate the return, and the return is the return. There is no uncertainty on returns. There are things that can move up and down and sideways or whatever, but the return is a return. We have the definition and we play by the definition, right? Another example is the time that it takes you to get from point A to point B, right? So I get in a car, my Uber or whatever, and I say, hey, I want to go to downtown Toronto, and I measure from the beginning I start to ride to the end when I get off the car, and that is that. Natural labels are inexpensive to obtain and may motivate a lot of machine learning projects. Now, there's a very nice result which comes from text, right? So let's say that we have this sentence. Natural ground truth labels or natural labels occur when the system can automatically evaluate or partially predict. So I can create an algorithm that will allow me to predict the next word in a sentence, right? So in this, let's say that this is my sample, I can say, wait, let's take 3 words as a window, right? So natural, ground, truth. And I want to predict the 4th one. Okay. So in this case, natural, ground, truth, the word labels becomes the label for these features. And then I move my window by 1 word. And then I say ground, truth, labels, or is the word that I want to predict. And then truth, labels, or natural is the word that I want to predict. Okay, so that is another form of natural labels. I don't need to do anything to my data. My data naturally lends itself to create those labels. Okay, recommender systems are the prime examples of natural labels. We will know if the recommendation was good if it was acted on, right? So Amazon produces a set of recommendations, and their machine learning algorithms will capture, right? Whenever you click on a recommendation, that was a good recommendation. It captured your attention, and the click in itself is the label. Now, there's a chance that we're browsing the Amazon website and we get distracted. The dog needs to be taken out. Okay. So I open up my Amazon account. I am looking at my recommendations. I'm about to click something, but then the dog comes by and says, "Hey, take me out," and we go for a walk, right? I come back and I close my browser, right? Was that, at what point do I say, "Hey, it took long enough, and I'm going to discard this as a negative label example," right? We need to we need to define what that feedback window is going to be. So in cases such as recommender systems, we need to have this parameter in mind and say a natural label will occur if I detect a click within the first 5 minutes that I show a recommendation, right? So now I have a parameter that will define my labels. And in the example that I was giving, maybe I return from walking my dog and I do actually click on the thing, but it happened 30 minutes after. That doesn't count as the label because I have defined a parameter that limits to 5 minutes. Okay, and that is part of the context of your problem. You just need to be clear as to how you defined these things. Natural labels are inferred from user behaviors like clicks, and ratings are known as behavioral labels. And behavioral labels can be explicit, right, as observed from user behavior, clip, upvote, rate, or implicit labels are inferred by non-behavior, for example, the ads that are not clicked. So that is where I say I didn't click on the link, and that is a negative label. Okay. Now, sometimes we don't have labels and we need to create them, right? So how do we do this? Okay. The first thing is something that is, in my opinion, a little misnomer. It's called weak supervision, right? So can we automate costly hand labeling? Well, sometimes we can use heuristics, right? We ask our experts, hey, how would you label this data? Oh, notice if this variable is above this number and that other variable is true, then the label will be red. Okay, I can encode these conditions and apply it to my data set. Okay, so if you are able to combine a number of heuristics and label your data, you will be getting fairly far into the weeds. Sometimes you will need to do this with expensive features to acquire, right? So you acquire a subset of data with these expensive features, you calculate the labels, and then you train a model not on the expensive features, but on the non-expensive features, right? There is a cost in acquiring data. And sometimes this is the reason why we go into weak supervision. If everything can be done with weak supervision, with heuristics, then there's no need to apply machine learning models, right? So you simply apply the rule and the heuristic will give you the label, full stop. Okay. Semi-supervision. It leverages certain structural assumptions to generate new labels of data. It is useful where the number of labels is limited. Sometimes we can only afford a limited amount of labels, and there's a couple of approaches that we can use. The first approach is called self-training, and we train a model So let's say that we have a sample of 1,000 observations that we want to label, and we only have labels for 100 of them. So we train a model on 100 of them, and then we apply it to a little more. So we apply it to 50 additional observations, right? Then we go in, we review if the labels are highly probable. So remember that we can produce a score and we can do something to that score to actually convert it to a probability. So we have a sufficiently high threshold. If we say, hey, if my algorithm is saying with 80% chance or more, this is going to be the label, then I keep it. And if that threshold is not met, then I declare it as a negative label, right? And then I repeat, right? Now I would have the original 100 samples labeled, and then with this procedure, I would have 50 more. I take 150 samples, train another algorithm, and repeat, and that 50 more observations, and then 50 more observations until I get to 1,000. Okay, this process can be automated, right? So you can automate all of these conditions, and ultimately, what you're saying is we will expand our labeling using machine learning algorithms. Okay. And a couple more approaches that can be thought of as semi-supervision are similarity and perturbation. So another approach is we have 100 samples that have been labeled, and in my feature space, I can calculate distances, right? So similar points, and I will make this assumption, similar points within a certain neighborhood, within a certain vicinity, there will be, they will receive the same labels, right? So it's almost like clustering, right? So anything that clusters together, they will tend to be the same, and I make the assumption if they're nearby, label them as such. And this could be convenient or it might be misleading. And the thing here is that you need to be judicious enough to actually understand if this is an appropriate way of thinking about your problem or not, because there's always a chance that your classes overlap and neighborhoods will not be a good assumption to make for your problem. Okay. A very similar approach is to generate synthetic data, right? I can perturb my data and generate more data. So I have 100 labels and I say, hey, let me add some random noise to my features, right? And if I don't add too much noise, I just create more features with additional labels. This last bit is kind of like the origin or the basis of a couple of techniques called mode analysis. And in olden days, they were very popular, and there's a few books and papers written on top of them, but I think that the practice is moving away from them. So, in my opinion, approach number one is very sensible. It's actually very useful. Approach number two is depends on the context, and approach number three, you probably want to stay a little away from that. Okay. Now let's talk. What do we mean by class overlap? The classes don't overlap. What overlaps is the position in the feature space of the observations. So the feature space is the space in which the features are defined, right? So think of it as a map. Imagine that your features are only two, X and Y, and they represent coordinates, right? And what we're trying to predict, as you will try to predict, are forest fires. Okay, so the label should be, is this thing on fire or not, right? And in that case, if 2 points are nearby together, it might be reasonable to think that if one thing is on fire, the other thing will also be on fire or catch fire, right? And if a thing is not on fire, the thing that is beside it will also not be on fire, right? So let's assume that these are positions of trees, right? And what we're trying to label is if the tree is on fire or not, right? And that is what I mean by proximity, right? In that context, it makes sense perhaps to make this assumption that similar things should be labeled together, or not very distant things should be labeled in the same way, and distant things should be labeled differently. Okay. Class imbalance. Class imbalance is something that is also very important to understand. Class imbalance happens when we have classes, but one or a few of the classes which are not very well represented in our sample, will be very important for us, right? So a patient that is sick with a certain disease, that disease may not happen very widely in the general population, right? But we are very interested in seeing if that disease is actually a positive case, right? Certain transaction is highly profitable and we will make a lot of money, but these transactions don't happen very often. But we're very interested in identifying those transactions, right? And so in life, generally the most interesting things don't happen very often. If things happen very often, they are not very interesting, right? So that's kind of like a very intuitive way of looking at it. Now, the problem is that our algorithms learn by examples. And if there are not very many examples, they won't learn very well. And we will need to do things to our algorithms, right? So to work with class imbalance and imbalanced labels, right? We will need to do a few things. We need to choose the right performance metric, and that is fundamental. That is all something that we always need to do. We can do data level methods, so change the data distribution to reduce the imbalance. So that is one thing that we can try. Probably want to leave that till the end. Or we can do algorithm level methods. That is something that will come out of the box in many of the algorithms that you will use. So to do this, I will need to discuss a bit of performance metrics. And I'm sure that you have seen this before, well, almost sure. And the object on the left-hand side is a confusion matrix. It is a matrix that summarizes the quality of my results, right? So this confusion matrix basically will say, in reality, I may have negative or positive cases. Let's assume that we're talking about a disease, right? There are certain people who don't have the disease. There are some people that will have the disease. And my algorithm, I train it, I evaluate it, and in my testing set, I will get positive and negative predictions. Some predicted negative values will actually be negative, right? We're very happy with those. Some predictive positive values will actually be positive, and we're also very happy with those, right? But then we have the other diagonal in which we have predicted negative values. We think that the person doesn't have the disease, but they actually do. Or the converse case, right? We think that the person may have the disease, but they actually don't have it. Okay, we want to make these numbers closer to zero, and we want to make these numbers non-zero, right? So as large as possible. How do we measure these things? Because we said if we want to optimize something, we want a number that has a single dimension. And in this picture, we have four numbers, right? So we need to reduce four numbers into a meaningful single dimensional number. Accuracy is the first thing that comes to mind. Now, these results are coming from a data set, the Give Me Some Credit data set, that has about 7% of positive cases. Okay, so an accuracy of 93% doesn't tell me anything. It doesn't tell me anything because if I have an algorithm that only says everything is a negative case, automatically I will have 93% accuracy, right? So achieving a 93% accuracy as defined as the number of true positives plus true negatives divided by the entire sample, it will not tell me anything. So an alternative is that we use something called recall and precision. Okay, so recall and precision are metrics. Recall will measure how many samples out of the total positive samples I actually labeled positive, right? So I cast a net and say, hey, bring me all the deceased cases, all of the cases that have a disease, and pull them in. And in that net, there will be positive and negative cases. But if I have all of the positive cases, my recall will be very high. Now, I said there were positive and negative cases. If there's only positive cases and all of the positive cases that I could have found are in there, then I will have both very high recall and very high precision, right? Now, if together with all of the positive cases, which gave me very high recall, I also bring quite a few negative cases, so my algorithm is kind of conservative, right? Then I will have low precision. So we want high recall and high precision, both. Okay. We may want to report both metrics, but still we need a single number. And the single number can be obtained by the F1 score. Okay, the F1 score is nothing other than 2 times precision times recall divided by the sum of precision and recall. So precision and recall will go from 0 to 100 to 0 to 1. If both numbers are 1, so it's going to be 1 times 1 equals 1 divided by 1 plus 1, which is equals to 2. This ratio will be 1/2 multiplied by 2. We will have the number 1. Okay, so if either or is low, it starts becoming closer to 0. The numerator will become closer to 0 and everything will collapse into 0. So F1 score is a nice combination that will give us what we want. However, in the definitions of precision and recall, there is nothing or there's very little information about the true negative cases, right? So we want to include true negative cases together with true positive cases. Yet another option could be the receiver operator characteristic. The receiver operator characteristic is a diagram, it's a graph object that relates the false positive rate and the true positive rate. Okay, the true positive rate I may have a definition. If not, I'll send you in the message. There's a correspondence between precision recall and true positive and false positive rate, but it's basically the amount of true positives by the total number of positives, and the false positives divided by the total amount of predictive positives. Right now, the idea here is very intuitive. It's actually a very nice idea. If we had a very good model, not a very good model, but if we had a perfect model, we would need a metric that tells me this is perfect. And that is the area under this curve. Now, how do we form this curve? We train an algorithm, we ask it to perform a series of predictions on our testing data or our validation set, and we rank order them by the score, right? The highest score comes at the very top and the lowest score comes at the very bottom. And then for each level where I can cut it, when I can draw a threshold, I actually draw a threshold, right? So anything, any observation that is above, that has a score above that threshold will be a positive, and any observation below that threshold will be a negative. Okay. When I have that definition, I can calculate my true positive rate and my false positive rate, and I mark a dot, right? And then I move my threshold, I perform the entire set of calculations again, and I mark another dot. Move my threshold, and so on and so forth until I complete my curve. If my classifier were perfect, my classifier would give me a shape that would be, where's my pencil? Something like this. Like a rotated L in this graph, right? And that is the perfection, right? That is something that doesn't exist, but we are aspiring to. So to compare all of these curves, what I can do is I can calculate the area under the curve, and this is my benchmark, right? So this is the perfect threshold, the perfect model, but every single line underneath has an area underneath it, and the area will be greater if the curve becomes similar to that rotated L. Okay, so we can use the area under the receiver operating characteristic curve to evaluate different different models. And this is a standard practice in many areas. I can tell you this is a standard practice, for example, in credit risk modeling. Okay. Now we have discussed cross entropy, so I kind of gave it away from the very beginning, but cross entropy is actually a very good performance metric that considers both the probability of a prediction or the score of a prediction. You can use probability of scores if you have them, conformal probabilities, and the class labels, right? And we now remember that we had this example at the very beginning of our lectures in which the characteristics of the log loss were very desirable. Okay, so the first thing to do is we need to select a good performance metric. If we have class imbalance, we said that choosing accuracy will be misleading because in this case we have very high false negatives, right? You can see the numbers. We don't want these, but we have also very high accuracy. We want to avoid that that situation, right? Now, there's a couple more things that we can do, and I'm going to spend a few more minutes, like 5 more minutes, just, and I'll conclude the lecture tonight. Class weight. Within your algorithms, there is a function that needs to be optimized. For a logistic regressor, for example, it will be something like a log likelihood. For a decision tree, it will be something like a Gini coefficient. For a neural net, it will be a loss function. Okay. So every algorithm is generally defined with an optimization problem within it. Now, there's an outer optimization problem that we are solving, right? We are comparing a logistic regression against a decision tree, against a neural net, and we need to use a standard metric. That is where the log loss enters, or the ROC-AUC, or the accuracy, if you will, right? That is something that we choose. The algorithm designer has chosen something else. Okay. Now, in the optimization that is happening within the algorithm, not in the general optimization that we run, but rather the one that is being run in the training exercise, we can modify the class weights in such a way that if the algorithm makes a mistake in a class that we care about, the minority class, it will acquire a very high weight, right? And if it makes a mistake in the majority class, we don't really care because we care about the minority class, okay? So you can follow a couple of approaches. The first approach is to ask your expert, what is the relative cost of making a mistake in the minority class versus a majority class, and they will tell you it's a 10-to-1 ratio or an 8-to-1 ratio or something along those lines. So you make one 8 times as large as the other, right? So that's a good informed class weight. If you do not know this, you can apply this formula that is an option inside Scikit-learn, and it will automatically calculate a reweighting scheme, right? And the formula is relatively simple. It's the number of total samples divided by the product of the number of classes times the class, the cardinality of the class that we're interested in. If this number is very small, because it's the minority class, this entire number will tend to be small. And in general, this ratio will tend to be large, right? If we have the majority class, this number and y will be large, and then the entire ratio will be small, and that is how this thing works, okay? The consequence of this is that some algorithms will be affected. Not all algorithms will be affected, right? The algorithms that are based on entropy, tree-based methods, will generally not be affected. What I'm showing in this left-hand side of the slides is a comparison against different weighting schemes. So I have a 1-to-2 weighting scheme, 1-to-1, sorry, and then 1-to-2, 1-to-4, 1-to-8, 1-to-16, 1-to-32, and then the automated rebalancing method that I just explained. Okay, so this means that every error weights the same. The minority class error weights twice, 4 times, 8 times, 16 times, and so on and so forth, as much as the majority class error. I can see here, I have produced 3 performance metrics, ROC, AUC, precision, and recall. And I have applied this through a decision tree model, a random forest model, a support vector model, and a logistic regression model, right? You can see that the tree and the random forest, both tree-based methods, don't have any impact. These guys don't care. Support vector machines and logistic regressors will care, right? And this is because they don't use entropy. They actually use something that resembles error. And as the algorithm, as we're assigning a greater weight to our minority class, we can see that we actually can get a bump in our ROC AUC performance metric, right? So the curve is becoming closer to the L curve. But our algorithms are also becoming more conservative. They are recalling a fair bit of the positive samples, but they are decreasing in precision. Okay, so so be careful when you apply these methods. These methods will induce this type of conservatism in the calculation, and whenever you apply it, you need to be aware of these results. Okay, and then the last 2 minutes is these techniques called SMOTE. You will come across them. They're implemented in scikit-learn and many other methods. And SMOTE is just basically a way of creating synthetic data. Okay, so synthetic data means data that we invent, and the procedure is relatively simple, right? I take 2 instances of the minority class, create a linear combination between them, then choose a random number, and that is where we place the new class, the new sample of the minority class. We do this several many times, and we are inventing new data points for the minority class. We are assuming that if they are near minority class members, they will also behave like a minority class. Addison is fundamentally the same idea, but it will privilege regions where there is overlap between the majority and the minority class. Because for most algorithms, if both classes are separate, they will not have any issues determining the boundary. The problems come when they overlap. Okay. Now, this was an old method. It used to be very popular, but I think that with the current more complex methods, we can actually get better results as long as we evaluate our classifiers correctly. So if we use conformal prediction methods to transform class scores into class probabilities, then we will get very good information about our complex models that will help us solve this issue. Okay. Now, when I say conformal or calibrated probabilities, I mean that whenever I get a prediction probability of 70%, it means that when I look into my validation samples, 70% of the time, they will be that class. Okay, so there is a conformity, there's a certain validity that we can obtain from our validation set results and the class probability that we are observing. That does not come out of the box of any method in scikit-learn. And in general, you should not assume that the class proba function that you get from scikit-learn will actually get you a calibrated probability. Okay. With this, we have covered everything that we wanted to cover in terms of theory today. On Tuesday next week, we're going to start once again with VS Code, go through some sampling methods, examining some samples, and we're going to continue with the modeling exercise. As well, with what we have seen today at the beginning of our class, you should be able to complete the first assignment. If you get stuck, of course, there is a working session tomorrow, and there's another work session on Saturday. Okay. Happy to take questions, Ritu, for sure.
Yeah. Can you walk us through the assignments? Assignment number 1.
Assignment number 1. Is there any other question before I walk you through assignment number 1?
Questions, but I think we need to read it before.
Sorry, no, I meant in general in the class. Hiroshi, please.
Jesus, thank you. Just quickly, way back when you were talking about the streaming sampling, you talked about replacing the numbers within streaming that you define.
Correct.
When you say replacing, are you replacing that? What do you mean by that exactly?
Oh, yeah. So in the reservoir is kind of like a box, right? And it has 100 slots, right? So you can place elements of your sample in any one of the 100 slots. Now, I'm just using the number 100 just to make it easier to understand. So anytime, once the box is complete and you have all of your 100 samples, data will continue flowing in. Okay. And anytime that a new observation comes in, you produce a random number and evaluate it against each one of the positions, right? And that is how you replace one of the samples that you used to have and you put in a new sample.
Okay.
And the thing is, you want to keep it fresh, right? You don't want data that occurred 2 years ago. You want something that occurred a few seconds ago. And that is how it works.
So you're taking a new stream sample out of the stream, put it into the box.
And
Instead, you take it out of the old one. Okay.
Exactly so. Exactly so. Okay. So let's look at the assignment. Okay. This notebook assumes that you have run the assignment, so you already have some features embedded in there. Load the assignment environment variables, so you know how to do this. Import the price data, use the glob to find a path. So you need to apply the glob function. We have discussed this a couple of times. You need to create a certain set of variables, high, low, range, and so on and so forth. You need to assign it to a new data frame, right? So you need to operate on the data frame, and you need to remember, of course, that you are operating in a grouped data frame. You need to group it by ticker and then perform all of the operations to create the lag, create the returns. You can take that from what we saw today. But in addition to that, I will ask you to do high minus low. That is generally called the range because that is a measure of volatility. If the difference between high and low is very large, right, it means that the stock moved a lot during the day. And that is a measure of risk. Once you do that, you will create a moving average, right, of the returns. Moving averages are very common. You want to see on average for the past 10 days, what was the return, right? So is the stock trending up? Is the stock trending down, right? Because if you have a positive average, it means that on average during the past 10 days, the stock gained. And if you have a negative moving average, the stock has declined. And I asked you a couple of think about your answer questions. And of course, there is submission information. That's basically it. I think it's a very simple assignment in the sense that most of it, you can take it from the class notes. And the last few instructions are meant for the people who want to shine. And that is the philosophy that I'm trying to follow, right? So most of it, you will be able to directly lift and shift or do a little modification, and then you should be able to solve it. But then the last few things, calculate the moving average and that sort of stuff will require you to do a little more experimentation. Does that make sense, Rito? Or do you need...
Yeah, moving average, I don't think we've done. That's fine, we'll try.
Yeah, that's part of the challenge, right? I mean, I cannot give you all of the responses. Come on. Okay. I saw a hand. Maybe there was an additional question. Maybe it was a cat.
No, I actually had my hands raised, but it's not related to the assignment. So I'm
Excellent.
not sure to ask. Yeah.
We're done with the assignment. I'm happy to take any other questions.
Okay, awesome. Are we going to cover how to get how to work with API?
Very little. We will work with MLflow's APIs, and we will use MLflow's SDK in Python. But we won't create an API, and we won't use it very extensively. I know I am preparing, and I am about to. Let me just pause the recording.